Okay, we are live.
Let me copy the streaming link and update it. Okay, I posted the links and I'm going to mute myself now.
Or if you have just joined the live streaming of this event, we will get started in a few more minutes to give everybody a chance to connect. Again, if you have just joined the live streaming, we will be starting soon, just giving everybody times to connect. Again, one last time, we will be starting in 1 minute. So please be patient for a little bit longer and we will start this session soon. All right. Welcome, everybody. Welcome to Orbit Camp 2022. We are excited you are here with us, and we're excited you are going through the modules and learning about multi-body dynamics and their application to trajectory design. I am Dr. Davide Guzzetti. I'm one of the voices behind Module 2 and Module 3 and some other videos in the lectures in the course. Together with me today, we have Dr. Kayla Martin.
Hello, I'm the other voice that you guys have heard on the course so far. And we're super excited to kick off our live streaming events today.
And with us today, also one of my graduate students, Datri Somavarapu, which is, I think, the voice in some of the lecture, but also the mastermind behind this year event. So a big thanks to Datri, and Datri, if you want to say hi.
Yes, welcome, and I hope you enjoy the camp and the seminars immensely. Thank you. And
finally, the reason why you're here today to attend Professor Koki Ho presentations about space logistics for cislunar and interplanetary space mission design. Professor Koki Ho is the recipient of multiple career awards as well as a professor at Georgia Tech. So thank you, Koki, for joining us today. Without further ado, I will let the stage to you. So whenever you're ready, feel free to share your slides and start your presentation.
Okay, hello everyone. You can hear me? Great. So thank you for the introduction. My name is Koki Ho. I am a professor at Georgia Tech. I'm a director of the Space System Optimization Group at Georgia Tech. So today, thank you very much for inviting me. I want to give a talk on the topic of space logistics and mission design, particularly some of the general grand challenge we have, and also some of the research we have done, as well as some of the future work that I think will be important. So just to start with a brief introduction of myself or my group at Georgia Tech. So like I said, I named my group as a Space Systems Optimization Group. What we do is to create optimization models and methods to tackle complex space mission design problems. And particularly relevant to today's talk, we have done some work that pioneered the logistics-driven modeling optimization in the space mission design field. So what I mean by logistics-driven is basically try to draw some inspiration from what we do in terrestrial logistics and come up with some method to tackle the complexity in space missions. As you know, the future space missions will be different from the old days where we had just a single satellite and a lot of resource just dedicated to that mission. And once that mission ends, we start over. We have a new satellite, and that satellite does its own mission, and so on. In the future, we may have multiple satellites working together, or we may have multiple missions that coordinated together to achieve some more ambitious goal. So there we are encountering some challenges of logistics, and we deal with this complex logistics problem on the ground every day, like what, for example, Amazon does, what FedEx does. They have a lot of challenge because of the complexity of the logistics and on the ground to deliver package, to make sure that all the transportation is lined up, and so on. So there are a lot of logistics challenges we are already tackling on the ground. So can we learn from those experiences and handle some of the new challenges that is unique in space exploration, especially unique in those growing space enterprise that can be significantly more complex than the traditional space missions. So I gave 3 examples here that we consider as a complex space mission problem. Of course, this is not a exhaustive list. This is just a few examples that I think is very important. The first one is about the human space exploration. So this is a figure. It's a little bit old now, but basically shows our journey to Mars. It's a NASA's plan, NASA's vision to basically consider a lot of different technology development and missions combined together for the common goal of sending human to Mars in the near future. So this, of course, involves some missions. For example, in Earth orbit, to some experiment that we do at the ISS, International Space Station, and they also include some missions in the space between Earth and the Moon, what we call cislunar space. Some missions that go to the Moon, surface of the Moon, for example, to get some resources there, and of course also missions that goes to Mars. And the missions to Mars can include some precursor mission that can be fully robotic, and then those missions can be followed by human mission to Mars. So basically, the point is that this is different from just sending one spacecraft to Mars and that's it. That it's not like that. It doesn't work in that way anymore. It involves a lot of different missions, and those missions are coordinated with each other. And each of them, of course, has its own mission goal, but we also have some common vision, common goal that we need to achieve through multiple missions. Now, that is one example where the logistics-driven modeling and optimization can be important. The second one, the middle one, shows the small-sat constellation. You may have heard this OneWeb or Starlink by SpaceX and other concept of constellation that comprise of hundreds or thousands of satellites in low Earth orbit. So those satellites, of course, need to be coordinated in an efficient and effective way so that they achieve some common goal. And those satellites can fail, of course, because we all have some mean time between failure associated with every component we have on these satellites, and how we make sure that they have sufficient spares, and how we make sure that we have a minimum interruption in the service even when some failure happens. How do we make sure that these satellites can be deorbited successfully after it ends its operations? So those are, of course, some of the logistics problem that becomes important because of this large scale of the constellation. The last one, this is attracting more and more attention recently, especially by DoD, Department of Defense, is on-orbit servicing, assembly, manufacturing. I think they now calling it in-space servicing, assembly, manufacturing. It's kind of a little bit a broader definition, but essentially we are talking about repairing some satellite or refueling some satellite. So even if something goes wrong on the spacecraft or it runs out of fuel, traditionally we just discard those satellites because we can't do anything with it. But if we have some capability to provide servicing, then we can extend the life of those satellites, or maybe do something new with those satellites, even after some malfunction happens on them. And we can also assemble different satellites and create a large architecture that wouldn't be able to fit in the launch vehicle, or maybe even manufacture. Right? We have 3D printing technology demonstrated on the International Space Station. Those can be potentially used for future manufacturing of spares or manufacturing of even satellites in space. Again, those can be really a game changer of future space exploration, but it also involves this logistics driven perspective, because now it's kind of literally logistics, right? How do we make sure that we have enough spares? How do we make sure this satellite will continue functioning, even not at ideal state, but still to satisfy the mission goal or satisfy the constraints we have. So those are all very interesting optimization problems. So today, given the the topic of this particular talk, I will be talking about this campaign level space exploration mission design in the cislunar space, and also beyond, for example, for Mars exploration. But I'm happy to also discuss the other two topics if there's any interest in the Q&A session, or maybe at another opportunity. Okay, so let me talk about. So actually, I prepared a pretty long slide deck. So I'll try to spend more time, given that the majority of the audience is undergrads. I'll spend a little bit more time on the introduction, and then I'll probably skip some of the details. But of course, I'm sure there are some of you who are very interested in the more details or some advanced stuff. Again, I'm happy to discuss during the Q&A, and I'm happy to share some of the technical papers with you if there's any interest. So assuming this topic is new to many of you, I will kind of start from some of the high-level discussion. The motivation behind logistics. I kind of already talked about some of this, but this is kind of a specific slide that have been used, I think, for probably more than 10 years, maybe, by different people. I'm just kind of adapting some of it and made some edits to that. So basically, when we think about space exploration, when we think about past or current space exploration, some of the represented missions in terms of human space exploration would be Apollo and the International Space Station. So if you think about the logistics paradigm that have been used for these missions, for Apollo, we use what we call carry-along strategy, which means that we carry everything we need to each mission. And once that mission ends, we basically move on to the next mission. We carry everything again. So there's really no, in a sense, logistics, because each mission was kind of independent. Even though we of course have some science goal that we want to achieve through all these missions, but if you look at the commodity flow, if you focus on the how we transport these payloads, for example, it's a relatively independent strategy, what we call carry-along strategy. And then ISS is kind of the opposite. So we have the ISS up there, and we carry what we need, and we even replace the crew through different missions. So now we have the ISS up there, and then we have multiple kind of nodes, origin nodes, that are basically providing the resupply for the station. So this is kind of the other extreme in terms of logistics paradigm. Now, when we think about the future space exploration, we need both, right? We will have multiple destinations, multiple origins. So the logistics network will be substantially more complex compared with the ISS or Apollo. So pure carry-along or resupply does not necessarily work efficiently anymore, or even effectively anymore. So there's a motivation to come up with a new strategic logistics paradigm, which can be a combination of carry-along and resupply or pre-positioning. And we also have a new set of technologies like for infrastructure in space, like the resource utilization and the program depot. So resource utilization, or sometimes it's called in situ resource utilization, ISRU, is essentially, it's like mining on the planet. So for example, there are concepts that have been proposed for mining on the moon. And this is like an oil field in space. So it generates the resource from the in situ environment. For example, you can generate resource from the soil of the moon or the regolith of the moon to generate propellant, like to generate oxygen, for example, which is often used as a part of the propellant for rockets. And on Mars, we have had a successful hardware demonstration of generating oxygen from the atmosphere on Mars. So that's the only successful ISRU demonstration so far, but we have others planned for future missions. Now, ISRU is definitely a key to future space missions. So basically, it can it means that you don't need to launch everything from the ground. You can get stuff from the in situ environment. But at the same time, this plant, of course, is not for free. It doesn't come for free. You need to pre-deploy those plants. You need to take into account this large plant mass and so on. So basically, you need to consider the cost associated with this ISRU plant. And propellant depot is another concept that again have been used, have been proposed for a long time. It's like a gas station in orbit. It stores propellant and sometimes even some reusable structures in space. There are different locations that can store those, that has been proposed as a potential storage location, like Lagrangian points or in Earth orbits and so on. But those propellant depot, of course, also required refuel mission by tanker from the Earth or from ISRU. And also storing the propellant in those propellant depot can lead to boil off, which means that you can kind of store your propellant there forever. So storing over a long time, you'll start to lose some of these. So the key question here is that all these technologies for space infrastructure, they are definitely a game changer, but they are effective and efficient only if their benefit will be larger than their cost, right? So there is a question whether these at the system level, at the campaign level, this technology actually will be paying off or not. So that is a question that cannot be answered easily. There are experts of those technologies that have been discussing, saying, for example, ISRU is effective because ISRU can generate this much propellant, for example, right? But that argument itself is not strong because then at the same time, how much does it cost to deploy those ISRU? So in order to answer this question, we really need to look at a campaign level strategy, which is why I've been using the word campaign level. So campaign here, I mean multiple missions. So we have multiple missions coordinating with each other for some common, for example, mission requirement or mission demand. And that is what I call campaign here. So we need to consider the entire campaign in order to answer the question whether this ISRU is actually effective or not, or propellant depot is effective or not. So that comes to this, academic field of space logistics. So I'm currently the chair of AWS Space Logistics Technical Committee, where we kind of discuss different technical topics associated with space logistics, including the definition of space logistics. And this is the latest definition we have. We define it as a theory and the practice of driving space system design for operability and supportability, and of managing the flow of materials, services, and information needed throughout the space system life cycle. So the key here is really that our goal is to make sure that space system have high operability and supportability. And what we deal with is a flow of material, services, and information. And particularly what I'll be talking about in this talk is the flow of materials. And we need to consider the entire space system lifecycle. We can't just look at one mission. We need to look at the entire lifecycle. So those are some of the keywords behind the space logistics, at least the way we define it. So the next two slides, I will be talking about some of the earlier studies in space logistics. Excuse me. One of the early studies in this field is by Dweck et al. At MIT. So that was, I think, early 2000s. So it's like, 15 years ago to 20 years ago. So at that time, there was a space program called Constellation Program by Bush administration. So this constellation doesn't mean satellite constellation. This constellation was a mission back to the moon and eventually back to send human to Mars. So for that mission, we basically had a lot of discussion about how we model the logistics. So that, I would say, that was one of the first space program that triggered a lot of the discussion related to space logistics, at least in the context of human space exploration. So what this Dweck et al. Did is to develop a software called SpaceNet, and it has different versions. It's SpaceNet 2.5 is probably one of the latest one, but still it probably hasn't been updated very frequently recently. But it's one of the older, one of the, I would say, original, or one of the traditional in a sense. It's not like super traditional, because all of this is happening over the past 20 years, but one of the traditional software that we can use for space logistics. And this software, it can be downloaded, by the way, from the website at the bottom here. So this software is modeling software. It models the space logistics with a discrete event simulation environment. And it performs demand analysis using a dynamic logistics model. And it can simulate the full campaign to quantify different measures of effectiveness. So this was kind of the starting point of a lot of space logistics research that have happened after that. So some other research that in space logistics, and those are mostly what I did in my grad school. By the way, I did my PhD with Dweck at MIT, and so there we kind of sometimes use that SpaceNet, and also sometimes we kind of developed our own tool to analyze different missions. So one of them, we looked into the program depot, how that can help the lunar exploration. The second example here is we consider space station logistics, especially we consider how the current space station operation can be coordinated with the logistics system, right? I mean, the cargo delivery vehicle for space station, we don't have that many options, and especially at that time we didn't have that many options. Now we have Dragon and others, but we are basically considering whether there's any kind of concurrent optimization that can happen between how we operate the space station and how we design and operate the logistics system. And there are some interesting trade-offs we can perform. And the last one here is, I don't know how many of you have heard of the program called, project called Mars One. It was proposed by Dutch nonprofit organization to send a human to Mars one way for I believe for a reality TV show. So at that time we looked into we basically leveraged some of the logistics tools we have developed, including the mission design, but also the life support system. And we applied those tools to this Mars One program. And so that was a kind of one of the very interesting and I would say successful integrated system analysis for space habitat and logistics. And it basically found some caveat of the plan Mars One had at that time, and we proposed some solution to those kind of caveat, so that the mission, basically we propose we propose several suggestions of the change to their missions so that they can be more feasible. So it got a lot of the media attention at the time. So that was again one of the successful example of space logistics related to more kind of real missions. So from here, I want to kind of talk about some of the specific research topics. Again, I won't go into detail, but if you have any questions, I'm happy to answer those. So I think one of the grand challenges in space logistics is really how do we generate optimal architecture and design for multi-mission space campaign? So we have talked about different way to model the campaign. We have talked about different way to analyze the campaign. But in reality, what we want to use these tools for is to come up with a campaign that we can implement in the future. So, and ideally come up with an optimal campaign. So how do we optimize such a space mission campaign, such a multi-mission space campaign? And those multi-mission space campaign will include both the deployment and utilization of the space infrastructure elements. So that's kind of the question that we want to answer. So basically what I mean is that we want to generate this entire, this is kind of sometimes called bar chart, but we want to generate this entire multi-mission scheduling problem, which includes the schedule, of course, also include how many launches, when to launch what from where to where, and also the trajectory choice, and whether we use high thrust or low thrust. Do we need staging? Do we need refueling? And how about the consumables? And how about spacecraft design itself? And do we need ISRU or not? So all these questions need to be answered. And what I want to show over the next 5 to 10 minutes is one way to answer this question, one way to generate this entire mission sequence given the exploration demands only. So we don't tell the optimizer the solution, we only tell the optimizer that, you know, what we want to achieve. And the optimizer will optimize this entire mission sequence and tell you the best way to achieve that requirement. So that's kind of one way, one ground challenge we're trying to tackle, basically to automate the mission sequence generation. Of course, in reality, we can't automate everything because there's always some part that required human coordination, human in the loop for the design. But we hope this can be one way to support the mission design practice and make that process more rigorous and also more efficient. So I'll talk about kind of 2 ways that we have tackled, and then the third I will talk about some others because I don't have time. I can't go into the details of all of them, but I'll talk about a few very briefly. So the first one, we looked into the integrated space campaign and the vehicle infrastructure design. So the way we tackle it is really, again, to get inspiration from the terrestrial logistics, where we consider the entire mission design problem as a network optimization problem. So here, the network will include this orbit as a node, and then we connect them using arcs so that we can solve this problem just like how FedEx optimized the transportation network. In addition, we can also consider the spacecraft model, and we can consider the infrastructure model as part of this integrated framework. So we can consider both the mission planning and the spacecraft design and the infrastructure design all together so that we can basically generate the entire mission from scratch. And the idea behind this is something called time-expanded dynamic generalized multi-community network flow. So this is the original version of a static generalized multi-community network flow was developed by Shimatsu. And in my PhD thesis, I basically developed an alternative version that can consider the dynamic mission sequence, which enable us to generate the entire mission sequence instead of just a snapshot. So this is kind of an extension of some of the multi-community flow network that we use for the terrestrial logistics optimization. again, I'll skip the details, but basically the idea is that we consider the flow with multiple commodities. And here the commodity, I mean the payload, vehicle, propellant, food, and so on, basically everything that flow over the network. So we consider them as commodities. We have constraints that will constrain the relationship between the commodity. For example, when you have a propellant, you need to have a propellant tank associated with that, and so on, right? All these constraints will be allocated. And then we have some demand we want to satisfy. We want to, for example, deliver something from the origin to destination, and we optimize and find the best way to do that. Probably I should skip this. So basically, this is just the optimization formulation. I wanted to kind of show it just for completeness, where we have the variables that flow over each pair of node. Basically, there are variables associated with each arc. We have constraints associated with each node, each arc, and so on. And this will basically be applied to every pair of nodes in the network. So it will be a quite large optimization problem. And in addition, like I said, we also need to consider this spacecraft and the infrastructure modeling, and we can consider a different way. There are different ways to model the sizing of spacecraft and infrastructure. This is just one way. We actually have come up with a better way to actually consider the multiple subsystem design and so on. But here again, I will skip the details for the interest of time. I will skip some more details. I'll show you one example. So this example is on, by the way, I'm happy to share the slide if there's any interest with this audience. So there's a case study here that we consider, which is like it's like a Apollo type lunar campaign, but we have a larger demand this time. And so we tell the optimizer that we want to send human crew to the moon and the back, and we also want to carry some more equipment, and we want to bring back some samples. So these are basically what this table is saying. So this is what we tell the optimizer, and we also give the optimizer some of the parameters for food consumption rate, water consumption rate, and all these things. And then we run the optimization, and let's see what comes up or comes out as a solution. For the single mission case, for example, we have this solution. We have this this is a 13-day mission where we send a mission to the low lunar orbit. We leave one stage there. We have the remaining stage to the moon, and on the way back we have a smaller stage that carries human crew, and that will dock with this stage that was left at low lunar orbit and comes back. And all this was found by the optimizer. We didn't tell the optimizer to, for example, let one stage waiting in low lunar orbit and so on. We just tell the optimizer that we need to send this stuff to the moon and bring this stuff back to the Earth. And the optimizer can optimize the size of each stages and optimize the entire sequence. And you may notice that this is kind of similar to what Apollo did, where they had one stage waiting in the low lunar orbit. But we didn't tell the optimizer to do that. The optimizer still came up with this kind of solution, which kind of demonstrate that how useful this kind of optimizer can be. And when we consider multiple missions, the optimizer now can consider the option of using the resource from the moon. In this case, 3-mission case, we basically repeat the same mission 3 times, but the optimizer says that let's not just repeat, we can send some resource plant to the moon and use some resource from the moon. That actually can be more effective, more efficient for this particular case. So instead of repeating the same thing 3 times, we actually have a better solution, which is to use a resource from the moon. And this optimizer considers the cost that associated with launching those plants to the moon and generate the time that's needed to generate this resource. And it will consider all these factors, and you may notice that the module sizing, the size is also bigger than the previous 1-mission case. Considering all these factors, this optimizer conclude that it's still better to use a resource from the moon. So that's kind of that kind of trade-off that kind of system level trade-off is something that the optimizer would be able to help. So traditionally, this kind of process have been done by human designer, thinking about different options and iteratively and so on. But this optimization can help with that, and in this particular case, it can reach a solution with 5 seconds on the 5 minutes on a regular desktop, which is quite fast. So this is quite encouraging. I want to show another case that basically tackle a different side of the challenge. So one of the perspective that we didn't tackle in the previous example is considering the low thrust spacecraft. So in the previous case, we consider a network, and we say, okay, in this network, we basically will optimize the mission over that network. And we just assume that the trajectory between each pair of nodes is kind of known, right? It's given in one way or another. For example, the delta V and time of flight is given. And that's okay for high thrust. You can solve Lambert problem between different 2 nodes, for example. That will give you some solution. You can use that as a starting point, or at least as a first order approximation. But for low thrust, it's not that simple, as you may be aware of. So for example, constant thrust propulsion system, it really, the time of flight and the propellant you need will really depends on what payload you carry. With the same propulsion stage, if you carry very large payload, you will follow a different trajectory than if you carry a very light payload, assuming you have the constant thrust, because the acceleration will be different. So the low thrust trajectory will be a completely different problem than how you handle the high thrust case. So that is the second problem. So can we use this electric propulsion, low thrust, and the high thrust chemical propulsion in combination in a campaign? So with the previous method cannot be used anymore, because previous method assumed the network is given. Here the network is not given, because network will depend on what you carry. So how do you still optimize it? So one of the kind of encouraging example, like why we need low thrust and high thrust together, is shown here. For example, we need a lot of fuel if we use high thrust. If we use low thrust, we only need a little bit of fuel, but it takes very long time. That's kind of the high level trade-off we need to do. So the idea is that we send human using high thrust, because we need to send human there within a very short time, given the radiation and other constraints. But we can send the propellant that's needed to send human using low thrust. So that's kind of the idea. So we use low thrust, and it can take time because we're just carrying propellant. We can drop those propellant in, for example, Lagrangian points or at low lunar orbit. And then maybe we can also send some additional propellant using high thrust. And then we have this crew using high thrust and go there and pick up those propellant and do whatever they want and come back. So that then this time you don't need to carry everything you need with you. You only need to carry the minimum, of course, with some redundancy, and then contingency propellant. And then you get the rest from this orbit depot that was launched previously using low thrust. And because low thrust is very efficient as a whole, you don't need to launch as much as you would need otherwise. So this is kind of the concept. Again, I will not talk about some of the details, but the idea is really to approximate this low thrust trajectory online. So we're building the network online using some approximation model instead of using a network that's given from a different module. So we're basically merging the trajectory calculation problem as part of this mission design, but using some approximation model. So one way to approximate is, in this case, we are considering the low cislunar. We use feedback control or Lyapunov feedback control, so-called Q law, and also using a circular restricted 3-body problem. Basically, the manifold that's associated with halo orbit, and we basically consider an optimal selection of this patch point that patches Q law solution and this manifold. so that we now consider the departure from the Earth orbit to the halo orbit in one sequence. And this is not the optimal solution because we didn't optimize this. We just use feedback controller and a manifold. But at least we have some research that demonstrate that this can approximate the optimal solution very well, very efficiently. And what we do is to calculate this for a different set of arcs, and then we create a piecewise linear model, and you integrate that piecewise linear model into the original optimization. And again, I will skip some of this, but we can, as a result, we can generate this kind of Pareto front, which basically we have this three objective function. One is a mass, a launch mass, and one is cargo time, and one is a crew time. So now we want to do the trade-off. So of course, if you increase the launch mass, we can deliver the stuff with a short time, and so on. So we have this kind of trade-off, and we can explore a variety of different solution points. This again is another example of considering the entire campaign, doing a variety of different trade-offs. I know I probably am running out of time, so these are some examples. So I'll probably just stop here. I have some other slides that can show different extensions, but the idea is really that by considering this space logistics idea, we can consider different missions coordinated for some common goal. So this is kind of expanding what we do in trajectory, which basically focus on one spacecraft going from one place to another place. But here we're talking about coordinating different missions, doing something all together. So that's kind of some interesting part of this research, and it also has a lot of potential. So thank you very much for your time. I'm happy to answer any questions. I'm happy to share this entire slide deck, which include a lot more than what I talked about. Thank you.
Thank you, Professor Ho. So for those of you who are watching right now, feel free to type in the questions in the chat that you might have. And I'll start off with a question from Matthew, whose question is about, in terms of math, would you say that mixed integer linear optimization is a big component of this work?
Yes, so definitely. So one of the, so I would say there are kind of two ways to answer that. So one is that some of the early work we did, basically the work I introduced here, is using mixed integer linear programming or mixed integer linear optimization, and that is because of the efficiency of solving this, and also because of the relatively simple network we have. Now, but if this basically assumes that we can approximate the model, spacecraft model or trajectory model using a linear or a piecewise linear function. But that's not necessarily true if we start to consider a higher fidelity problem. So actually, one of the extensions I was about to introduce is to consider this in a more mixed integer nonlinear programming perspective. But instead of solving everything together, we break down the problem, we decompose the problem into mixed integer quadratic programming and a nonlinear programming. And we can solve all of them in using, one way to do that is using augmented Lagrangian coordination. So that basically the short answer is that there are different ways to solve it. Mixed integer linear programming is one way of solving that, and that is a way that I introduced in this talk. But there are many other ways, and this is again one of the work I'm happy to share if there's any interest. That goes a little bit beyond mixed integer linear programming.
Absolutely. This question is from Becca. When you are writing your optimization code, do you have a coding language preference? Is it MATLAB, Python, or something else? What's your preference?
Yes, so that's interesting because when I was a grad student, Python was not as popular as it is today. So I used MATLAB at the time, but nowadays Python is way more popular, and my students are all using Python. So yeah, nowadays probably Python is more common. But I mean, I personally don't have preference. I think one way or another, if you can make it work.
So most of this work was done in Python then, or was it done in MATLAB?
all the work I talked about today was done in Python.
Okay, awesome. Another question, when you're looking at the model, when you're doing the last example you gave, when you're doing a design trajectory for low thrust or impulsive thrust, are you doing like 2-body models? Or are you doing a high fidelity model? Where are you starting with the optimization scheme? So are you starting from like a 2-body solution and then going up to a higher fidelity model? Or how does that work in your optimization scheme?
Yeah, so for this particular case, we are mostly interested in the orbit from Earth orbit to halo orbit, for example. Right? Of course, there are different halo orbit in EM01, EM2, and so on. But we basically use Q load, which is again a feedback control load that takes you from the Earth orbit to this manifold path. Actually, it's the other way around for various reasons. But from this manifold path point back to the Earth orbit, and this is done because it's a feedback control load, so we can run it in 2-body, 3-body, whatever body you want, because it's just a feedback control that takes you following the equation, governing equation motion, and then the rest, this pink curve is a coast arc on the manifold, which is again defined in the circular restricted 3-body problem. So in that sense, it's all done in the 3-body dynamics. But again, this is not an optimized solution. If you want to optimize this in 3-body problem, that's a whole different story.
That's totally true. So Michael asks, have you considered nuclear thermal propulsions in this work, such as DARPA's Draco, as part of your logistics model, or are you focusing more on current assets that we have available?
Yeah, so in my PhD thesis, which I didn't show here because it's a little bit old work, but there we considered nuclear thermal rocket. So nuclear thermal rocket can be effective, but of course there's this issue with technology readiness level, and also the other consideration associated with that. So for the work that I have shown today, we haven't considered. In fact, after my PhD, I didn't really spend a lot of time working on that. But all the tools that we have developed is it's general. So once we have all the details of propulsion technology parameters, we can just put in, and the same optimization should still work. It's just that the result I have shown today didn't include that.
Michael also was wondering who your advisor was at MIT.
I was Olivier Debec.
Okay, awesome. Thank you. And then another person asked, how long does it take these simulations to run?
Which simulation?
Let's go with the case here.
Okay, yes. In this case, we have computed different time of flight, final mass, initial mass. For all these cases, it takes about 30 minutes. So it's not that long. That's because we use approximation, use Q-law.
And we have another question. In this particular case here, are you doing the restricted 3-body problem in 3D or 2D? So I guess they're asking about planar motion of the moon or not.
I think this case was done in 3D, but yeah, I mean, it's halo orbit, so 3D, yes.
But it's definitely makes it harder to solve.
That's right. But again, this is not really optimizing anything. This is just propagation, so that helps.
And then Terry asked a question about the challenge would be if we're trying to implement a sustainable LEO network for small satellites. If you're going to do 6G for small satellites, what are some of the challenges that would be in place to do a LEO network?
Yeah, there will be a lot. So, for example, so of course we need to consider how many satellites we need to make sure that we have a high, reliable service, right? It's not just a minimum demonstration. We need to have a sufficient redundancy in case something fails. Yeah, and also that means there will be many satellites. So that means we need to consider orbital debris problem. So what happens if those satellites start to retire? How we handle those spares? How do we even launch those satellites to space? Because we don't have a launcher that can carry thousands of satellites, for example. So we need to launch them in stages. And while we're launching them, we still need to make profit, and we still need to make sure that the satellites that are on orbit is providing some service from the very beginning. So Starlink is kind of doing. It's kind of one example that I think is relatively successful, but there are still a lot of challenges because we're still kind of pioneering this field as a community.
So Nicholas, well, I guess we had one other question about space debris and whether or not you consider it a serious problem.
Yes, so it kind of depends on what you mean by serious, but yes, it is a serious problem for many satellite operators, especially in some orbit that are very crowded. So we definitely need to do something with it, including identifying where they are. And sometimes that can already resolve a lot of challenges, but identifying the space debris definitely is important. It's a field called space situation awareness, and then how do we make sure that we don't generate additional debris? I mean, it's impossible to not generate any debris, but how do we minimize the debris we generate? And then how do we actively remove those debris, which will be a little bit harder.
Absolutely. So shifting to a different topic, Nicholas noticed that your cislunar graphs didn't include GTOs or HEEOs, so but they seem maybe possibly useful. So when you're doing your optimization, is there some sort of optimal solution that would be sharing responsibility between the Earth and the Moon rather than the cases that you looked at?
Yeah, there can be other cases that we may have missed, and definitely, highly elliptical orbit. I mean, GTO is actually considered, but any other, highly elliptical orbit we haven't considered. So yeah, there are definitely some additional orbit that can provide more optimal solution that we just didn't explore in this particular example.
In terms of low thrust missions, I guess I thought it was really interesting how you're merging low thrust and traditional impulsive mission design planning into one optimizer, which is really awesome. Another person asks, how useful do you think that low energy trajectories are going to be once we start the Artemis program and moon exploration?
Yeah, I think they will be important. So whether we want to use them for human or not is a different question, because it takes time to go anywhere if you want to use low energy transfer. But they can be very useful for delivering some cargo or some satellites, and and they can generate some very creative solution that you wouldn't think of, that can reach very high efficiency in terms of a fuel use. So definitely there are a lot of in this problem, again, optimizing this low energy transfer is a classical trajectory design problem that have been explored a lot, and still there are a lot to be explored. So definitely those are some interesting open questions that we can look into.
In terms of optimization and creating an optimizer, what is an implementation challenge that is often overlooked?
I see. So I don't know if it's overlooked or not, but what's important is the validation. So sorry, my Siri just tried to answer this. So I think it's important to make sure that the model we're using is valid, and that's often a challenge for academic research because we don't have access to a lot of data. But still, it's important for us to basically all those optimization, whatever that you input as a parameters will directly impact the quality of the solution you get. Because if you just put in some random parameters, then the solution will be useless. So you need to make sure that what goes into the optimization is a valid model or valid assumptions. And whenever we convey those results to, for example, key decision makers, we need to make sure to clearly define the assumptions and so on. And I think that's kind of one of the important part. And I think it's not necessarily overlooked. I think everybody, at the key decision-making position understand that, but it's just something that we need to keep in mind so that we don't necessarily, overreact to the numbers we get, but rather what is, the relationship between what we give the model and what we get, from the models.
And then one last question, which kind of ties into that validation piece that you were just talking about. When you set up these models, did you deal with depreciation of the assets involved, or was that something that you didn't include in your model?
We did consider, for example, the maintenance that will be needed. So it's kind of, I don't know if it's exactly depreciation or not, but for example, when we have ISRU, we want to use it over a long time, we need to consider the maintenance that's needed. And same for spacecraft. If you have some reusable spacecraft, we of course can't use the same spacecraft again without any additional costs associated with that. We need to have some we need to have some maintenance effort going on. So that is considered. Now, whether that's the best assumption or not, again, that would depend on the decision makers. And if we have some additional assumptions we need to make the depreciation more realistic, then that probably need to be considered. But at this moment, this kind of additional maintenance costs, maintenance mass is the only way we considered.
Great. Well, that is all the time that we have today. So I just want to say thank you, Professor Ho, for taking time to talk with us today. It was an amazing talk and a really interesting subject that we don't really think about a lot when we're doing mission designing. And so we've got a couple more questions that have come in, but I don't think we'll have time to answer them right away. But maybe if you've got some time, you can post a reply and we can post that on our Canvas discussion board. For those who have joined us on the live stream, thank you so much for taking time to listen to this talk, and we're looking forward to seeing you guys later in this week.
Thank you very much for inviting me, and I hope you enjoyed the talk.